Okay, so as I said, today is all about high-performance Python, and we start with actually finding the part. We start with the task on finding out which part of the program is slow. That process is called profiling. So in particular, I'll show you 3 different ways how you can profile. There's timing, there's profiling, and then line-by-line profiling. So as a general rule, there's a famous quote by Ken Beck. It says, first make it work, then make it right, and then make it fast. So the point here is that the optimization step should really be the last step in a process. You first have to make sure that your program actually doesn't crash, right? Then you need to focus on that it provides the correct answers. And then once you've achieved these 2 things, then you can sit down and think about how can I make it fast. So that's something really important to keep in mind. So that means before we start optimizing our code, we need to also find out which parts of the code are actually the ones that need to be optimized. Right? So that's a very important process. And that process is called profiling. And it allows us to measure resources that are used by sections of the program. So resources that might be of interest are the amount of CPU that is being used, but it might also be the amount of RAM that is being used by a section of the program. It might also be that you're interested in optimizing the disk input-output, right? So you might also want to do profiling with respect to the disk I/O or network I/O. So profiling is a very broad way of finding out the bottlenecks of a program. But we will focus on CPU profiling today. So we want to find out, imagine you have a huge amount of code, and all you know is that it takes forever. How do you find out which section of the code consumes all that time? So when you want to do profiling, the most important thing is that you start simple. Don't use the most complex techniques to find out what's going wrong. Start with the most simplest techniques and then switch to something more complex if it's required. And the order in which, or what I typically do in terms of profiling, the simplest step that I do is manual timing. So I'll explain all these in a second. So the first thing is manual timing. If that is too complex or it doesn't get you any further, then I start using the timeit module. And then even that doesn't help, then I use the cprofile module or the line-by-line profiler, which I'm going to show you. So let's look at a case study to introduce these concepts. Let's imagine we have a grid, a 2-dimensional grid, and we have data points on all these, on all the grid nodes, and that these data points are stored in a 2-dimensional NumPy array A. So this A here holds values of the grid points. And then what we would like to do is we would like to loop over all these grid points and call a function on each of them, right, to evaluate a function on all the different coordinates in that grid. So here's an implementation. I implemented as a class. So the class is called grid2d. It takes in the dimensions of the grid, so the smallest x coordinate, the largest x coordinate, and then the distance, the grid distance. And then I use the numpy arange function to create all the x coordinates and all the y coordinates. So this class members here, x core and y core, they store all the x coordinates and the y coordinates of the grid. And then I implemented a grid loop function, and essentially what it does, it creates a new numpy array with called A. So this will store the values, the function values at each grid cell. So it has the same, it is a 2-dimensional array with the same size as the coordinates that we have. And then what I do is I loop over all the x coordinates, I extract the x coordinate, then I loop over all the y coordinates, I extract the y coordinate, and then I call the function fxy that is passed in as an argument up here, and then store the result in the associated index of that numpy array. Okay, so that's our test case that we're going to look at now. So this is how you use it. You create a new grid. So this is how you use it. You first create a new grid. You specify how fine should the distance be between the coordinates. And then you can, once you have it, then you can compute the grid values of this function. So you define a function that you want to have evaluated. In this case, it's sin is x times y plus y. And then you call the grid loop function and pass in the function that you want to evaluate. And if you run this, it takes some time, and then it returns the values. So let me just go back, and actually we can do this live. So let's see if this actually works. So there it goes. So now it computes, and now it's done. Okay. So the first thing if you want to find out which parts of the code take time here is to do a manual timing. And the way you do manual timing is really simple. You start a timer before the code that you want to investigate, and then you check the time before you start the code that you want to evaluate. Then you check the time again after the code has been evaluated, and then you print out the difference, right? So you just this is kind of wall clock timing. You check what is the time now, then you run the code, and then you check the time again, take the difference, and that tells you how long that piece of code took. And so you can use the time module to do exactly that. So it's a very simple concept, but it's very powerful. Just some guidelines. If you have very, very simple statements that you want to test, so for example, if you just want to test the timing of adding two numbers, the problem is that the time function here has only an accuracy of, I'm actually not exactly sure how accurate it is, but there's kind of a limited accuracy. So in order to get reliable timings, you need to execute simple statements many, many times. Otherwise you don't get, you might just get noise. So put simple statements in a loop and execute them many times, maybe 1 million times, to get a reliable output. Also make sure that you're not running other programs at the same time on your computer when you do timings, right? Because otherwise you might just, your CPU might be busy with other stuff. So make sure that you have kind of ideally an idle machine when you do timings. And then run your timing test multiple times and choose the smallest value. Okay, so there's a question, why not take the average value? So you could do the timing test multiple times and just take the average. But why, do you see a good reason why we shouldn't use the average value, but instead the smallest? So the reason is that, again, we might measure some noise because maybe suddenly our operating system decided to tidy up the RAM at that particular moment when we run our test, right? So there might be some of our experiments might be artificially delayed because of operating system stuff. But we are interested in kind of the best case. What is our code? How fast can our code be executed in the best possible case? That's why we perform the experiment multiple times and take the smallest measurement value that we can achieve. There will be there will be a lower limit. There will be a limit where we just can't go lower, and that's what we're interested in. So also, a side note here, so there's two different ways on how you can measure time. There's the wall clock time, and that is what time.time gives you back. So this is literally what you get if you were sitting there with your wall clock and kind of just measured and program starts now and then program ends now, right? There's another thing, it's called the CPU time, and that you can get with time.clock. And that tells you how much time was actually used, how much time of the CPU you actually used. There's a difference here. So for example, if you're loading in a big file, if your program loads in a big file, right, that doesn't actually take much CPU time, but instead it might still take a long wall clock time because you're waiting for the hard drive to get in all the data, right? But your CPU actually doesn't have to do anything. So here you can choose a little bit on what you want to measure, so that you're aware. So let's do this in our case study. So we have two big things that we have two potential slow parts in our program. It's the grid 2D, so the initialization of the grid that might be slow. But it might also be this g.grid loop myfunc call that might be slow. Right? So remember, it took about 2 seconds or so. So one of them might take a significant amount of time. So let's time these separately and let's figure out how long they take. So here we have, so here is the timing of the grid to the initialization. So I perform this test 4 times. And I always start the timer, then I end the timer, and in between I initialize the grid. And then I show how long this experiment took. So when I run this, you get something like this. So there's 3 experiments, and you can see they roughly take, well, I take the smallest value, so it's 1 to the power of minus 5 seconds. Right? So probably this is fairly fast. So this is probably not the causing. This is probably not the problem. Here's the same thing now. Now I again run the experiment 3 times, and I call the grid loop function I time the grid loop function. And so let's see how long this takes. So here we have significant times, 2.3 seconds, 2.3 seconds, 2.3 seconds. Okay, so clearly it's the grid loop function that is taking time here. It's not the initialization. Okay, so that's how you do it manually. There's a module called timeit that makes it more convenient to measure the CPU time of small code snippets. The usage is very simple. You import the timeit module, and then you call the timeit function in it, and it takes 2 arguments. It takes the statement that you want to have benchmarked. So in this case, it's just the increment of a variable a. And then you can pass in a setup argument that provides you on how the variable a should be at its starting point. And so this timeit module works particularly well for these small code statements. And it wraps it automatically in a loop. And by default, it executes a million times and then returns the accumulated output. So I can run this, and it tells you, okay, for a million increments, it took 0.14 seconds. So sometimes a million times might take too much time. So then you can also specify how often you actually want to have this command executed. So in this case, it's roughly 1,000 times faster. Then finally, timeit also has a repeat argument. So here this is the idea that you should perform each experiment multiple times. So in this case, it would repeat the experiment 5 times and print out the timings for each individual experiment. And so really what you should do now, you should take the minimum of this, right? So this is now the best possible case. Okay, so for user-defined functions, so the problem with timeit is that it works in its own scope. So variables that you defined in your program are not immediately available in the timeit statement. So in particular, if we now want to, if we want to time our grid loop function, if you just tried it without any special treatment, it would not work because this variable g is not available in the statement. But there's a trick. You can import it. So both g and myfunc would not be available because they're variables that are declared outside the scope of the timeit. But you can fix that in the setup by just importing these 2 functions from the main module. So the main module in this case is the program itself. So by typing in from main import g and myfunc, then these 2 variables will be available in the statement. So this is how you can time your own functions. So it takes some time, and then it will probably should return us something with 2.5 seconds. Yeah, here we go. 2.2 seconds. Okay, so that's already gave us a lot more, but now maybe let's look a bit more into detail on what's actually wrong with the quit loop function. At the moment, we just know that's the quit loop function that is slow. And so there's a module called cProfile that allows us to see, that prints out statistics, how often certain parts of a program were executed and how long these parts took. And this cProfile is kind of the most common package that is being used. So the usage is very simple. You just, when you run a script, you can just profile it automatically by using the -m cProfile statement. And then it will automatically run, collect statistics while the program is running. Alternatively, you can run it inline as a module inside your Python program. So for that, you import the cProfile module. Then you create a new cProfile object. And then you use that object to run the function that you want to have profiled. So in this case, it's the quit loop myfunc function. And then this result object has the statistics stored. And then you can just dump them out. So we can run this. So this last line actually just stores the result into a file, but we don't see anything yet. But now we can use the res.printstat statement, and that will now print out the statistics of that program. So it looks quite messy at first, but essentially the important parts are, so here are some columns that are important, the number of calls and so on. I'll explain this in a second. And here each row is one particular function. Each row represents one function. And so the important rows here are the quit loop function and the myfunc. So these are the functions that I'm interested in. The rest down here doesn't really matter. It's just internal stuff. Okay, so let's see what we have for these two rows. So remember, this is one line here. It's just printed over 2 lines. So we can see, so the quit loop function is called exactly once. And so n calls shows you how often this function was called. Then total time is the total time spent in the given function, excluding time made in the calls to subfunctions. So this means the quit loop function took about 1 second, while 2.225 seconds were spent in the myfunc functions. Okay, and then cumulative time. This column here shows you the cumulative time spent in this and all subfunctions. Right? So essentially, this 3.235 seconds is these two numbers here added, because quit loop calls myfunc. And you can see myfunc was called about 1 million times here. Okay? So this gives you kind of a more statistical overview of what's going on. And we see that quite a lot of time was spent in the myfunc function here. Okay, you can also use the pstats module if you want to. You can have a lot more control over this. You can kind of sort these rows. You can sort after certain columns and so on and so forth. So what have we learned so far? We learned that the quit initialization isn't really the big bottleneck. It's the quit loop call. And the quit loop function itself contributes roughly to 1/3 of the total runtime. And then inside the quit loop, we call this myfunc function. And these calls contribute roughly to 2/3 of the total runtime. Okay, so this is what we have so far. So if you look now into the myfunc function, it's a fairly straightforward implementation. It's just a function definition, and we call a sign as an addition. So maybe there's nothing obvious that we can do here. But what about this quit loop that at least contributes to 1/3 of the runtime? So here we see it's quite a complex code. So this is just the implementation shown again. It's quite long and complex. So it would be really useful if we could know how much time was spent in every line of that code here, so that we can identify which line is the one that takes so much time. So for that, we have something called the line profiler. And essentially what it does, it inspects the time that is spent in each line of a Python function and then prints out an annotated version of the code. So you'll have the code, and then next to the code you'll see how much time was spent in each line. So the way you use it is, well, you first install it using conda. You just type in conda install line profiler. And then you decorate the function that you're interested in. So decorating just means above the definition you add this function you add this decorator add profile, and that will automatically wrap the function and collect the statistics, the line statistics for it. So you change your code so that you have this profiler annotation here, and then you run the program for the benchmark, and this is the command that you have to run it with. So there's a current prof command that you need to use. So we can do that here. So I've done this for our quit2d function. So it takes some time. And here we go. This is the output that we see. And so now you can see on the right-hand side, we have each line of that function printed. So again, keep in mind that this is over multiple lines, but this is our function definition, and then we have all the different lines. And then in here, you can see how often this is the number of hits, so how often was this line called. So in particular, if you look at this function, this assignment here where we call the function, this was called 1,000,000 times, right, for each coordinate in our grid. Then we can see how much time was spent here in milliseconds in a cumulative for that function. Then we can see how much time was spent for each call of that function, and then the total percentage of the time. So here we can clearly see that it's these last, if you look at the percentage of the time, right, so most of that is just 0, so it's not significant. It's the last 3 lines here that contribute to almost all of the total runtime. And these are the ones where we extract the coordinates and where we loop over the inner coordinates and where we evaluate that function, right? So it's these 3 lines that are critical in our performance. So the conclusion is a significant amount of the time is spent in the loops and in the indexing. Okay, so how can we, knowing now this, what would you suggest to improve the performance of the code? Yeah? Yeah. Yeah, okay. So there could be something with using in range, you mean? Okay.
Yeah, not using in range, but try to look over the list instead.
Oh yeah, okay, yes. So we could, instead of working on indices, we could work on the elements itself. Yeah, so that's one, yeah. Another idea, yeah? Yeah, so there's vectorization, right? So that's a really good one. So the first thing is we should kind of avoid indexing, but the next step is always vectorization. So let's try this. So here's a vectorized version of that implementation. So now I've avoided, so this is the new quit loop implementation. Now I avoided indexing completely, right? So there's no loops here anymore. And instead I make use of the fact that this f is a vectorized function. So I can just pass in the coordinates as numpy arrays, both for x and y. So this is the vectorized version. And so now we can compare on how much of a difference it made. So this is our vectorized implementation. And so I timed it again using the timeit. I think it's over 5 experiments in the minimum. So now this took 0.03 seconds. And now if you look at our original implementation again, .3 seconds. Okay, so that was if you work it out, it's probably roughly a 70 times speed improvements. Okay, so the important part here was really to find out what are the slow parts in your program, and then you can try to make it faster. Any questions regarding timing? It's all clear? Maybe? Good. Okay, so now we know how to find out the slow parts of the program, and we know some ways on how to improve it using NumPy and vectorization, but sometimes that just isn't enough. Maybe you have a complex function that you can't vectorize or you don't want to vectorize, and for these cases, there's something called mixed program. And mixed program allows us to mix different programming languages. So the idea is that we can have the Python code for the high-level user interfaces, and then we can implement the slow parts of the program in a compiled language like C. And so the reason is, well, Python might be sometimes slow for numerical computing. So for example, if you look at a very similar case that we have, it's essentially exactly the same thing that we had just now. So we have a NumPy array, and we want to fill it with function values. Now, if you look at the timings of various different implementations, so this is normalized. If a Fortran or C or C++ version roughly takes a time of 1, then the NumPy vectorized evaluation will be roughly 3 times slower. Then if you implement it with a normal Python loop, it will be, and you use the optimized math.sinus, then it will be roughly 140 times slower. And then if you use the NumPy version, this should be the other way around. Then it will be, so the normal Python version will be 350 times slower, and the NumPy version will be 140 times slower. So even with all our Python tricks, right, we will still be slightly slower than a C version. And so sometimes it's really important that we get the best possible performance. So as conclusion, so Python loops over arrays are always slow. So NumPy vectorization may be sufficient for some cases, but sometimes it's not sufficient, and also sometimes it's much, much easier to just implement standard loops using C or Fortran. So why is it that these compiled languages are so much faster? So the reason is that when you compile in advance, you can do various optimizations that Python can't do. And so these compilers, the C, C++, and Fortran compilers, they've been around for many, many decades, for quite a few decades. And they've been optimized over these decades to produce as fast as possible code. Another reason is that when you compile in a C program or C++ program, you provide information about the type that the variables have. And knowing the types allow the compiler to do very aggressive optimizations in advance, which makes the program so fast. So for example, it can do optimizations like code inlining. So if you have a function like the quit loop function that calls another function 1,000,000 times, the compiler might decide to just, instead of actually calling the function, it just copies the code of that function inside the loop, right? And that allows the program to avoid a function call. It can do loop unrolling, so instead of actually calling a loop, it just copies the code many, many times, and so on and so forth. So there's various optimizations that you can do in compiled languages that you can't do in dynamic languages like Python. So in Python, right, we don't have a compiler, so we can't do that. We do not declare the types of variables, so the program has to be prepared to work with any possible type that we have in Python. We can't do inlining, we can't do loop unrolling, and so as a consequence, even a simple function like this, function call like this, it's probably quite inefficient in compared to Python, because the program, when you call this function, right, you first have to, the Python interpreter needs to see, as soon as it's in here, right, it needs to see, okay, what types are my variables A and B? So what does it mean to actually add these two objects and so on and so forth? So there's a lot of checking going on before Python can actually execute the addition of these two variables here. Okay, so if we want to mix different programming languages, there's different tools that we have available. And essentially, there's two strategies. We can either extend Python or we can embed Python. So by extending Python, I mean that we have a Python program and we use libraries or functions written in another language. Right? So maybe you have a C program and you want a C library and you want to make use of functions of that library inside your Python code. Or, embedding is exactly the other way around. So sometimes you have a big Python, a big C project, and you would like to have a Python interpreter within that C project. Right, so that's embedding. So we only consider extending Python. So we kind of live in our Python world, and we would like to call out to C functions. So there's two big use cases for doing that. The first one is if you want to access functions in existing libraries that are written in C or C++. So rather than re-implementing a code, you would like to just use an existing code. The second use case is if you have a slow part in your Python program and you would like to migrate that code to a C implementation and then just call out the C implementation. So there's different ways on how you can do it. The most general, but the most, in a way, annoying way of doing it is to write the wrapper code yourself. So the wrapper code is exactly that code that that wraps a C function into a Python function and makes it available to the Python interpreter. So there's a Python C API that allows you to do exactly that. And it's a very, very general, a very low-level approach of wrapping existing C code. So the result is that it's really time-consuming and with significant overhead, and I don't think anyone does it anymore. So we have much, much better tools by now. There's C types. So this is actually something, C types are a part of the standard library. So there's no need to install additional dependencies. And it's a little bit better than writing the wrapper code by hand, but it's still a lot of overhead. So the resulting code is still quite non-readable and quite lengthy. And then we have Cython. So Cython is something that is an external package and is something that you will also use in your exercise. So Cython is basically Python extended with elements of C. So I'll show this to you after the break. So in Cython, we basically get a language that is something in between Python and C. So we can use, in Cython, you can specify the type of variables. You can say that something is an integer. You can say that something is a double, and so on and so forth. And so the trick here is that by providing all this information, Cython can compile the program and make it automatically available as a Python module. So Cython code needs to be compiled, and by compiling it, it can make use of all the type information, and still you will be able to use it just as a normal Python module. And Cython has a lot of advanced tools and possibilities beyond that basic usage. And then there's Number. Number is, again, something that you'll use. And Number is basically, it's almost like magic. So what it does, it runs your normal Python code, and at runtime, it checks if you call a function, so you can mark certain functions in Number. And when you're running your Python code, it realizes what are the functions that you're calling it and how are you calling it. So it checks the types of the variables that you're passing into a function, right? Then it has the type information, and from that it will automatically, while the program is running, it will generate a C implementation, generate the wrapper code for that C implementation, then load in that, compile it as a Python module, load in that Python module. Instead of running the original Python function, it will then run the C-compiled Python module. So this is what is called just-in-time compilation. So you don't realize you call the Python program just as if it was a normal Python function, but really what's going on in the background is that it generates C code and compiles the C code for the specific types that you're calling it with, and then you get the performance of C without having to specify, or with almost no overhead for the programmer. So the advantage is it's almost fully automatic. The kind of in-between is almost like magic, which sometimes can make it a bit more tricky if you do debugging. So if things work, it's great. But if things don't work, it might be a bit more tricky. And then really just a minor disadvantage is that you have to have external dependencies, and it has a lot of advanced technologies. So it uses the LLVM compiler and so on and so forth. So it's there's much more overhead than just a normal Python interpreter. Okay, any questions so far? No? Let's have a break, and then after the break we'll start with Scyther.